Okay, so hi everyone, welcome to review session 6. Um, there's honestly, so I've been told the policy is that quizzes have that's stuff on the quiz is basically just what was on your homework, and there's honestly not too much new content on the homework. So today's might be a bit shorter, just because you guys haven't really gotten into capacitors yet, so there's not too much for me to go over. I'll go over them anyway, but the stuff on the homework did not involve like actual what I would think of as capacitor questions. So I'll probably be a bit more brief with capacitors, and then just spend the majority of the time doing more complicated op-amp questions. Like I might go over one of the ones from your homework, and just do other op-amp questions. But yeah. So op amps, I did went over those last time. So if for those watching the YouTube video, if you're curious about those, go watch the last video. I'm going to do practice problems today, but I won't go over like the intro to them. Just watch the previous video. However, I'll go over capacitors. So a capacitor, as you all learned in physics class, is basically you can think of it as two parallel plates with a gap between them. And what happens is when you connect a voltage source to it, current will flow, or if you're being particular, you have electrons. Oh my God, my Apple Pencil hates me today. Come on. Why does it do this? It's not even dead, is it? Oh, it is dead. Ooh, ooh, that's bad. Okay. You can't use it while it's charging. Okay, give me a second. Okay, maybe it's fine. Okay, so and when you connect to a voltage source, you have in real life, you have electrons flowing to this plate, which will make it negative, and then as this charges up with electrons, electrons will go out of that plate, making this side more positive. Of course, since we are electrical engineers, or we are engineers, we think of it as positive charges flowing here and them flowing out of that side. And basically what happens is that this plate will charge up until the voltage across the capacitor is equal to the voltage of the input. So you have enough charges accumulated up here and depleted down here that the voltage is the same for V in as it is for VC. And then current will stop flowing. This is described explicitly as that the current of the capacitor is equal to the capacitance times the derivative of the voltage, I believe. Let me make sure I'm right about that. I think that's it. I equals C dV dt. Yeah, yeah. So what this is saying is the current flowing the current flowing is a function of the voltage changing. What this also means is that if the voltage is not changing, then there is no current flowing. The consequence of this is that when you first connect a capacitor to a circuit, so if we have what you'll see in this class is like a switch where it can be in, say, two positions. Um, how do I do this well? You have a switch, let's just say it's like this, right? And let's say this starts with a VC of 0 volts, and this is V in, and then we connect the switch. What'll happen is right as it is connected, we can think of the capacitor as an open as a short circuit. So it's going to let as much current as it wants flow through. And that's because the dV/dt is basically infinite at that point, right? If you think of the voltage across this capacitor, before that switch is open, it's 0. And then when the switch is closed, since it gets connected to that voltage source, you have kind of like if you're thinking about the voltage with respect to time, right? The derivative of the voltage here is basically infinite. And so that would mean that you have as much current as possible flowing through the capacitor. However, as the capacitor charges up, And I don't really know why I'm writing in red. I just started writing in red and I'm still going. So as the capacitor charges up, it approaches, uh, by it, I mean VC approaches V in, which means that dV dt approaches zero, which means that the current goes to zero. What this looks like, so the basic form for a capacitor equation is that when you connect the voltage like this, right, this will correspond with the capacitor having a exponential approach to that V in. You'll probably learn this in class as like VC of t equals, what is it? It's like for just a basic thing in series here, it'll be like VC of t times or V, no, it's V, yeah, VC of like infinity times 1 minus e to the negative t over tau. Um, and what this is, right? This is just a negative exponential, so that looks like that approaching 1, and then when you multiply it by this, it gets you the shape you want. But basically, the TLDR of this is that a capacitor, this is the main thing. And since this is here, this would be an open circuit. So basically, at t equals 0 or when something changes, uh, the capacitor is a wire, and as t goes to infinity, capacitor is an open circuit, which makes sense because it is physically two parallel plates, right? Like if we go back to thinking of it as two parallel plates as we did up here, like this looks like an open circuit because it is an open circuit. So hopefully that's all review to you. I'll go over more capacitor questions next week. Probably I'll do like an example here. But that's kind of the gist. If you understand what capacitors are and how they work, and that they will charge to the voltage applied to them, then you can get most of the stuff in this class. Yeah. So let's see. And I can give the more explicit version of that VC equation that I gave. Again, I don't think you'll really need that for this quiz because it wasn't on the homework. But the most explicit version is that VC of t equals VC of infinity. So this is what it will be when the capacitor is an open circuit plus VC of 0 minus VC of infinity. So this is how much the difference is between the beginning of the capacitor and like the end of, so like between the capacitor's voltage at 0 and the capacitor's voltage at the end. And then that times that e to the negative t over tau. Tau is a time constant which describes how fast this rises, and tau is equal to the resistance times the capacitance. And the resistance is basically the Thevenin equivalent resistance that the capacitor sees. And yeah, I'll touch on that in a minute, but or actually I might not for this lecture because again, I'm not like doing actual capacitor questions because all that was on the homework was just like looking at it at time it goes to infinity. So yeah. They said that the only thing that would be on the quizzes is the stuff that's on the homework. So I'm gonna go with that. So the other thing is just op amps. The homework had a lot of op amp questions, so I imagine that the quiz will also be a lot of op amp questions. Again, don't know for sure, but like you had 4 op amp questions on this homework, so surely you just have complicated op amp questions on this quiz. That would make the most sense. Yeah. Okay. So I'll start by doing the last op amp question on the homework just because it was kind of complex. And I think that doing this is kind of the most straightforward way I can really drive home what you do with these questions. So I will take a minute to draw this because it's kind of big. Oh, that looks bad. Okay. So as I'm sure you are all aware, this looks very complicated. However, in the same way that I described it in the last review session, you really approach these all the exact same way. And they're all pretty straightforward if you know the kind of approach you should use. Need to label them all with values now. 4 ohms, 5 volts. Probably should have just copy and pasted the image in. That would have been much faster, but I'm already this far and I will not change it now. So this question is basically just find V out, right? You all should have done this on your homework. Let me actually go grab my calculator before I get into this too far. Um, yeah. So the way we want to do this, if I'm looking at this, I say, okay, we need to find V out, which means we need to find this node because this node is connected to V out, so we have to write a node equation here. However, to find this node, we need to find this node and this node. And to do that, we need to find here and here and here and here. So basically, the idea is just start with the most basic inputs and then start with these two, and then oh, that's gonna look weird, and then go to here. So to start, we'll find, I'll call this V out 1, V out 2, and then we have V out, actual V out. So I'll start with this one on top. Remember, VP equals VM. That's the key thing. Since these are in a negative feedback kind of orientation, where the output is connected back to the negative side, the op amps will always drive the inputs until VP equals VN. So I'll start up here, right? VP is 0 volts, so VN will also be driven to 0 volts. Now, if we do a node at N, remember, since there's a wire here, this is all VM, right? So it has 4 directions. Even if this direction has 0 amps, so we can just ignore it. But if we do a node equation, there will be all of these directions to look at, right? So I'll say at VN1, we have VN1 minus 5 volts. So VN1 minus 5 volts, that's that bottom path over 4 ohms, plus VN1 minus 3 volts over 2 ohms, right? So we have here, here, and then last but not least, we have VN1 minus V out 1 over 4 ohms equals 0. And then if we solve this, right, if we plug in 0 for all of these, or 0 for what we have here, right, we end up with VN1 over 4 equals 5 over 4 plus 3. Oh, wait, no. Actually, yeah. Minus 5 over 4 minus 3 over 2 minus Yeah, it's just that, I think. Right? Because 0, 0, and then Vn1 minus V out. Yeah, minus, yep. Yeah, I think that's right. So then if we plug this into our calculator, we have come on, minus 5 over 4, minus 3 over 2, and then times 4, we get negative 11. So let's write that. Vn1 equals negative 11 volts. So we found one of these, which means once we have this, we can do a node here. However, we first need to find out, okay, what is the voltage going to be here? And for that, we have to find V out too, because that's connected to the plus side of this, right? So moving right along, um, now we have to solve this op amp. And we do it in much the same way. So remember, there's no current going into these inputs. So that means even though there's a resistor here, there's no voltage drop over this resistor since I is 0, so there's no voltage drop. So here, we're just going to have 5 volts. So I'll write that. I'll do this one in blue. So this is 5 volts, which tells us that this is 5 volts, which means all of this is 5 volts. So now, again, if we do a um, if we do a node at n, or at Vn, so at Vn2, we're going to have Vn2. I keep doing that. Vn2 minus 0 over 3 plus Vn2 minus V out 2 over 2 equals 0. And this is actually, if you remember, this is the non-inverting amplifier. The non-inverting amp where the gain ends up being like 1 plus R2 over R1 or something like that. But we're going to find that in a sec. So Vn, right, we're going to end up with 5 over 3 plus 5 over 2 equals V out 2 over 2. We plug that in, 5 over 3 plus 5 over 2, and then multiply that by 2. Let me make sure I'm doing this right. Yeah, we end up with V out 2 equals 25 over 3 or 8.33 volts. So now we found this point, or we found V out 1 and we found V out 2. So now we move on to the third op amp, right? So first, as we talked about last time, we want to find which side is kind of independent of V out, which in most cases is going to be VP. So if we know V out 2, then we need to find VP. There's two ways we can look at this. We can either do a node at VP, and so we'd have this current out and this current out, and then you solve for VP. Or you could look at it as a voltage divider where this is like a voltage source with V out 2, and then you'd have a voltage divider here between 6 and 2 ohms. Just because it's kind of faster, I'll do the voltage divider approach. So if we're trying to find VP, I'll just call this one actually VP. So VP is going to equal V out 2 times 2 over 2 plus 6, right? Because that's the voltage divider equation. And so that's going to be 8.3 times 1/4, or 8.3 over 4, which gets us 2.08 kind of 2.083. Yeah. So that's our VP. And then our Vn is the same, right? So Vn equals VP. And so now if we do a node at Vn, it's going to be same thing we've done before. It's going to be Vn minus V out 1, that's going to the left, over 6 ohms, plus Vn minus V out over 4 ohms equals 0. And now let's solve for V out, leaving the rest of these all the same. So if we do that, we're going to get Vn over 6 plus Vn. I can write this a bit nicer. Nah, that one. Vn over 6 minus V out 1 over 6 plus Vn over 4 equals V out over 4. So then if we plug things in, we know Vn is 2.083 over 6 plus 2.083 over 4 plus, and then we have V out 1, which we found earlier, is negative 11 over 6, right? So then if we know that that's equal to V out over 4, we can plug this all into a calculator, multiply by 4. So we have, just do that. So the answer times 1/6 plus 1/4, and then minus 11 over 6. Multiply that by 4. I messed up somewhere. Um, what did I do? Um, wait, I made some silly mistake somewhere. Give me a second. Hmm. Yeah, yeah, minus n. Yeah, yeah. I have that here, but I'm missing something because it's supposed to be 10 and I'm getting negative, or it's supposed to be like 10.8.
I think it's because I think it says it's minus VOL, so it'd be like minus negative
Oh,
11.
yeah, you're right. Okay. Yeah. Yeah. Thank you. Okay. Yeah, so that's minus minus, it becomes a plus. And that times. Okay. Okay, so I had this and then this and that times 4. Yeah, okay. Thank you very much. Because it's, I'll write that in more explicitly. Minus minus. Okay. Okay, and then that would get us V out equals 10.81 volts. And that's how you do it. So again, as with basically all op-amp questions, generally you're going to find VP because VP, or you're going to find the VP and then use the VP to know VN and then do a node at VN relating the output to things you know. And then once you have V out, you go on to the next stage where again you start by like finding your VP based on your voltage source or your whatever the input is to VP. Once you have VP, then you have VN, and then you relate VN to your output using a node equation, and then you have your output. So it's pretty straightforward. I didn't have to do too much math here. Yeah. And frankly, you're not going to get anything more complicated than this on a quiz because you don't have that much time. And yeah, there's not really much more like complicated questions you can even do. On a quiz, just to make sure you know what you're talking about, they might say, okay, what's the power dissipated in this resistor? In that case, it's still the exact same question. Since you don't actually do a node at Vn or at V out, right? You only do a node at Vn, you're relating it to just V out. So this resistor has no effect on the actual value of V out. So what you do here is you would find V out and then say, okay, the power of the 3 ohm resistor is just V out squared over R, which would just be 10.81 squared over 3. And then that would be your final answer. So if it's ever asking you to do that with like an op-amp question, it's just find V out and then find the power directly from that, which in this case would be 38.95 watts, which is a lot of power, actually. I don't know if you guys have noticed, but in your lab, you're using like much bigger resistors. The resistors you have in the lab are rated for a quarter watt. So if you give it more than a quarter watt, it'll burn up. So for a resistor, if you had a 3 ohm resistor rated for a quarter watt and you tried to pump 10 volts through it, it would just immediately explode. So sometimes I'll get quiz answers where someone writes like 2000 watts, and I'm like, that is the amount of power like like 10 computers would use. And it's just not realistic. So it's good to have like an idea of how big a watt is. In terms of like the circuits that you're doing in the lab, a watt is a lot of power. So yeah. Okay, I'm just gonna do, and I'll go over the last question on the homework as well, because that one just kind of shows like basic capacitor stuff. So this question is asking, you have a bunch of capacitors in a circuit, and what would the voltage be across these capacitors under DC conditions, which means like as time goes to infinity when the capacitors are just acting as a open circuit. Okay. So we have these four capacitors, C1, C2, C3, and C4. And the question is basically saying, as time goes to infinity, what is V1, V2, V3, and V4? And so to do that, we just think of these as open circuits. So just imagine there was an open wire here, and then we solve the circuit basically. So we find the voltage here, we find the voltage here, find the voltage here, and here, and then based on that, we can just kind of say what they are. You can think of it as like, okay, if we're looking at this capacitor, what's the voltage difference between here and here? So the things that we want to keep in mind here, since these are open circuits, right? Things we can point out is that the voltage here, since there's no current flowing through here, since this is an open circuit, right? The voltage at C2 is going to be the same as the voltage here, and the same as the voltage here because there's no current flowing that way. And this is all like the same as the voltage there, right? And if we define the bottom part as 0 volts, then this tells us that V1 equals V2, and that's going to be whatever the voltage is at this node here. For V3, well, actually, let's start with V4. V4 is just going to be the voltage at that node there, V4, right? Because that's the difference between here and ground. If this is an open circuit, you can imagine there's like nothing here. And so it's just asking, okay, what is the voltage? What is the voltage here? Since it's an open circuit, there's no current flowing down. So we have V4. And then V3, if we look, is the difference between this point and this point. Because you have a plus here and a minus here. You can just imagine like, okay, if I was using a voltmeter and I wanted to see the voltage across this 15K, that's going to be what the voltage would be across that capacitor. So we can even say V3 is going to be equal to V1 minus V4, since this is V1 equals V2, and that's V4. Yeah. So really, we only need to find V1 and V4. And we can just do that by doing some node equations. So for example, V1. At V1, I'll draw these in blue. We only actually have two two things going on. We got the down in the right, because remember, there's no current flowing through here, and there's no current flowing through here. And so in total, there's going to be no current flowing to the left at all. That means we only have that path and that path to worry about, since again, there's no current flowing up there. So V1, we're going to have V1 minus 15 over 5K plus V1 minus V4 over 15K equals 0. And that'll get us 3V1 minus, this is a K, not a Yeah. 3v1 minus 45 plus v1 minus v4 equals 0, which turns into 4v1 minus v4 equals 45. And then at v2, we're going to have um, v4 minus v1 over 15. So that's the same one we've already looked at. And then the other one is going to be v4 minus 0 over 10k equals 0. Multiply by 30k. Yeah, that would work. So then we have 2v4 minus 2v1 plus 3v4 equals 0. And that'll turn into 5v4 minus 2v1 equals 0. And then if we want to solve this, let me rearrange this so it looks better. It would be minus 2v1 plus 5v4. If you add 2 times this equation to the other one, we're going to get the v4s will cancel, and we'll get 4v4 equals 45. So we're going to do 45 over 12 or over 4, which I should be able to do in my head, but I don't want to, which I think I also messed up. That's not a number that I remember seeing in the homework. Um, where did I go wrong? Is it not 45? Hmm, where did I go wrong here? Feel silly. Because it should be 50. Wait, no. 15, 10, 33. Yeah. Yeah. Messed up the algebra somewhere. So, yeah. 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 What did I do? I don't even know. In the second equation, when I multiplied by 2, oh, yeah, I didn't multiply the 5, I think, right? Yeah. Is that it? Yeah, yeah, yeah. Okay. Thank you. Thank you, Chase. My fault. Didn't look at the comments soon enough. Okay, yeah, so 5 minus 1, then you get 9 V4. Okay, then V4 equals 45 over 9, which is 5 volts, which is correct. Okay, so now that we have V4, um, we can plug this into our equations from before to find V1. So if we have 4 or 4, 5, 4V1, 4V1 minus 5 equals 4V5 or 45, right? Then 4v1 equals 50, v1 equals 12.5 volts, right? And that's also v2. And then last but not least, v3 equals v1 minus v4. So it's going to be 12.5 minus 5, and that gets us 7.5 volts. And so that would be our final answers. Boop-a-boo, boop-a-boo, and there. Okay, I'm making all the algebra mistakes today. But hopefully you get the point. The point is that as time goes to infinity, this is just an open circuit. They're all open circuits. You know how to deal with open circuits, just pretend there's no wire there. And then it works. Yeah. I'm also just gonna do a normal capacitor question because this is something that you'll have to do next week. And like there's maybe they'll put it on a quiz because they technically put capacitors on the quiz. They like shouldn't, but we'll see. Um, let's see. Yeah. So this is a bit complicated. I don't know if you've done anything like this yet, but this gives a good illustration of my point from earlier. And the units for capacitance is farads, which is probably some guy's name. Probably the guy who first characterized capacitors. Anyway, so this is saying find VC of t. And if we remember, VC of t equals, um, we go back to here, that equation. So VC of infinity plus VC of 0 minus VC of infinity times e to the negative t over tau, where tau is equal to RC. So for this question, what we need to find then is we need to find VC of infinity, VC of 0, and tau. So let's start with, oh, and this switches at time equals 0. So with this kind of question, you're going to assume that the circuit has been in this state for a long time, which means that at the start of the question, for the VC of 0, um, for the VC of 0, we can assume that this is an open circuit. I actually should revise my, like this is kind of true, but not quite. The bigger point is that the voltage cannot change instantly because you think about it like the plates have to take time to charge and discharge. So the real point is that when this switch changes, so when the switch goes from here to here, so before the switch moves, the capacitor is charged up to some voltage VC at this point, right? And then after the switch changes to go up here, now it's connected to this current source and no longer connected to here. Now what we're going to see happen is that the voltage will approach some other value. However, it starts at what our VC of 0 minus was. But this is like the point there. It's that when the switch changes, the voltage does not change instantly. So that's the point there. But what that looks like is basically we just have to solve the circuit twice and find VC of 0 and VC of infinity, where we just have the switch in the two different states, and for both states, we assume that the capacitor is an open circuit. So for VC of 0, that's before the switch has moved, we can ignore the entire left half of the circuit and just solve for the voltage across that capacitor, which I will write as an open circuit. Forgive my horrendous drawing here. And so if you look at this, this is actually just a voltage divider where VC of 0, since it's in parallel with that 8 ohm, is going to be equal to the 8 ohm. And so that will be 24 volts, the input, times 8 over 8 plus 4, which is 2/3. 2/3 of 24 is 16 volts, right? Then for VC of infinity, after that switch has closed, right, we're going to have a new circuit, which looks like this. And there's two ways in my mind you could do this. You could either take these two resistors in parallel and then V equals IR, or you could Thevenin equivalent this side and then do a voltage divider how I did in the past in the first part. Just to be different, I'm gonna take these two in parallel. So the if we think about it that way, right, we're going to have the current source, some R equivalent, and then we're finding VC of infinity is the same as the voltage across that R equivalent. So R equivalent is going to be 8 times 24 over 8 plus 24, which is 8. Come on. 8 times 24 over 8 plus 24 is 6. So then the voltage is going to be IR, which is just 4 times 6, which is 24. Pretty cool, right? So fun. So that's going to be our VC of infinity. Remember, what this is saying is that basically, if this capacitor wasn't here at all, this circuit would have this point be 24 volts, right? So as time goes to infinity and this capacitor ends up acting more like an open circuit, that's saying that eventually this capacitor will charge up to 24 volts. That's 4 volts. Last but not least, we have to find the tau. So the tau is going to be the basically Thevenin equivalent resistance from the perspective of that capacitor times the capacitance value. So this is actually very straightforward for us since we already found this kind of version of the circuit from the perspective of the capacitor. So if we call like this A and B and we're trying to find the Thevenin equivalent resistance, it's just going to be Req, right? Hopefully that's pretty straightforward. So I'm just going to say tau is equal to R times C, where R is going to be 6 and C is 1/18th as it was given in the problem. Um, so you end up getting that tau equals 1/3. Now, if we plug all this into our equation, we get VC of t equals VC of infinity, which is 24, plus 16 minus 24 times e to the negative t over 1/3. If we simplify this a bit, we're going to get 24 minus 8 e to the negative 3t. And that would be in the unit is volts. So this might be something that'll be more on your next quiz. I can do another example problem next week. But one way to kind of double check that you did this equation right is if, okay, if we think about graphing this equation we just got with time and voltage. At 0 volts, or at time equals 0, this is going to be equal to 1, because e to the 0 is 1. So it's going to be 24 minus 8 at time equals 0, which would get us 16 volts, right? And that makes sense because we just found that VC of 0 is 16 volts. So that should line up. And then as t goes to infinity, right? As t goes to infinity, this is going to go to e to the negative infinity. E to the negative infinity is 0. So eventually this term is going to stop mattering, and that means VC of infinity is going to be 24 volts, exactly what we expect. And then basically the e term, since it's an exponential, what it's saying is that it just takes some time to get there. So we have some horizontal asymptote, and what we're going to see is after this circuit changes, it's going to go from its initial state and asymptotically approach that 24 volts. And the rate of this is described by that tau equals 1/3. So that's the idea with the capacitor. You can always double check your work by seeing if your time equals 0 and your time equals infinity is what you expected. Yeah. Again, I this probably isn't on your quiz, but I feel like it kind of should be. I don't really know why they didn't put this on your homework. I feel like there wasn't really anything new on the homework, but maybe they're just being nice to you guys, I suppose. But I felt like it's good to talk about here because you are talking about capacitors now. But again, if we're going off the idea that the only stuff that'll be on the quiz is what's on the homework, then the only capacitor question you should get is something like this. But that feels really easy, so I'm kind of a bit confused about that. But since I still have 15 minutes left, I'll do another like complicated op amp question, I think. Yeah, let me find a good one. Um, yeah, I'll do this one. This one like looks scary, but it's not that bad. Yeah. Mhm. So, so this is one of those questions where you just have to think about how you could kind of redraw the circuit to make it make a bit more sense to you, or just look at the connections very directly and make sure you're not messing up. And this was actually drawn like this, which makes it look a bit more confusing, but it's still exactly the same. So here we have 3 volts, 9 volts, 5K, 4K, 2K, and 6K, and 4K. And this question is just find V out. So, as I've said many times, you first just kind of find VP and then say VP equals Vn, and then do a node equation at Vn, and then you can find V out. So, that means we want to start by finding VP. But you might look at this and say, oh, but it's like kind of connected to the rest of the circuit. But the key thing here is that this point is defined as 9 volts by that voltage source, right? So what that means is that no matter what's happening up here, this point's going to be 9 volts. So as far as we're concerned, this could be drawn as a 9-volt source going here, and then an entirely separate 9-volt source going here. And the circuit would still be exactly the same because the voltage source is telling you that, okay, we have 9 volts here. Doesn't matter what's going on over here. The gist is that VP is not related to V out. So what that tells us is we can just do what we normally do. We have VP, and at VP, we can do a node equation, or we could do a voltage divider. You'll get the same answer. Um, but if we do a node equation, we get VP minus 9 over 6K plus VP minus 0 over 4K equals 0. We're going to get VP over 6, or if I'm doing this in the kind of the easiest way to plug into your calculator, we're going to get VP times 1/6 plus 1/4 equals 9 over 6. And then if we plug that into my calculator, we take 9 over 6 and then multiply it by, or divide it by, in parentheses, 1/6 plus 1/4. We get VP equals 3.6 volts. And that is also Vn. Next up, we're going to do a node at Vn. And if we look, Vn is all of this, right? So we're going to have 3 parts of Vn of this equation. We're going to have the 5K, the 2K, and the 4K. You have to make sure you look at all of them because since this is all one wire, this is all Vn. So it's going to be 3 terms. So we get Vn minus 9 over 2K plus Vn minus 3 volts over 5K plus Vn minus V out over 4K equals 0. Um, One thing I've noticed some people getting tripped up on is when you have like kilo ohm resistors, I see some people just like end up making math errors. If you're doing a node equation, you have a k in all the denominators. You can just pretend it's not there. If you were to multiply this by 1,000, they would all go away since there's 0 on the other side. So just kind of ignore them. It's fine. Um, of course, if you had one resistor that was like 50 ohms and the rest of them were like 1k ohm, then you can't quite do that. But basically just don't mess up the math, don't overthink it. If you want to plug this in as 2000 into your calculator, you'll end up getting the same thing, but it can be easier to just leave it in this form. Anyway, what we're going to end up getting from this is that V out over 4K. We just take this part and move it over preemptively. That is going to equal, I'll do it in the same way I did before, Vn times 1 over 2 plus 1 over 5. So that's here and here, plus 1 over 4 What's that? And then minus 9 over 2 minus 3 over 5. So then if we know Vn, right? Vn is 3.6. We're going to have 3.6 times all that minus that equals V out over 4K. And really, I left this as a K, but didn't make the others. Okay, so over 4. So then if we just evaluate the entire section on the left, so we have 3.6 times in parentheses 1/2 plus 1/5 plus 1/4, and then minus 9 over 2 minus 3 over 5. We get that and then that. Make sure I'm doing this right. Yeah. So we'll end up with minus 1.68 equals V out over 4, which tells us that V out is going to be negative 6.72 volts. So again, pretty straightforward. Just make sure you don't get tripped up by things like this, where you have things connected in odd ways. Make sure you're always thinking, okay, find VP, and then that's VN, and then you're good to go. Yeah. I only have 5 minutes left, which isn't really time to do another question, so I'll take a second. Does anyone have any questions or anything they want me to touch on in these last 5 minutes? If not, then I will just end the thing now. Okay then. Good luck on your quiz tomorrow. Make sure you understand that capacitors are open circuits at like as time goes to infinity, or at DC as they say. And yeah, good luck. See you then. Bye bye.